Today, it is our great privilege that the 9th annual Ramanujan Memorial Lecture will be delivered by a dynamic and illustrious mathematician, Dr. NIKHIL Srivastava, who has joined us online. Dr. Srivastava is an associate professor of mathematics at University of California, Berkeley. First of all, our heartiest congratulations to Dr. Srivastava for being awarded the prestigious Cyprian Foyers Prize 2021 in operator theory by the American Mathematical Society for solving the 62-year-old long-standing question on the Carrison-Singer problem and Ramanujan graphs. The Ramanujan College, and in fact, the whole nation is elated with your remarkable achievement. Congratulations again. Dr. Srivastava attended Union College in Schenectady, New York, graduating summa cum laude with a Bachelor of Science degree in Mathematics and Computer Science in 2005. He received a PhD in Computer Science from Yale University in 2010. His dissertation was called Spectral Sparsification and Restricted Invertibility. After completing his postdoctoral fellowship at the Princeton University, Dr. Srivastava moved to Microsoft Research India in 2012, where he stayed until 2014 before moving to Berkeley. Dr. Srivastava's research interests include theoretical computer science, algebraic graph theory, random matrices, asymptotic convex geometry, and geometry of polynomials. In 2013, together with Adam Marcus and Daniel Spillman, he provided a positive solution to the famous paving problem in operator theory formulated by Richard Caddison and Isidore Singer in 1959, a result that was awarded the 2014 George Polya Prize. He is also the recipient of the Michael and Sheila Held Prize 2021, awarded by the National Academy of Sciences, and the Alfred P. Solon Research Fellowship 2016. Dr. Srivastava is widely published in many reputed international journals, and among the many invited talks delivered by him is the prestigious lecture delivered by him at the International Congress of Mathematics in Seoul in 2014. It is our great pleasure and honor to have you with us, and we invite you to deliver the 9th annual Ramanujan Memorial Lecture on physical metaphors for graphs.
So, hi everyone. So thank you very much for that very warm introduction. And thank you to Professor Agarwal for inviting me here. It's been already a great pleasure. To be here even virtually. I wish I could have come in person, but I ended up getting a flu over the weekend, so I decided to come remotely. It's been wonderful to hear about all the developments in the college over the last 10 years and the amazing success of its teacher training program, the absolutely massive reach of that program. I really enjoyed listening to the musical performance and watching the dance performance. I really wish I could have been there in person for that. It's going to be hard for my lecture to compete with those. And it's a pleasure to be in the presence of Santosh Yadavji, even personally, even virtually, and I look forward to hearing her address. So yeah, let me share my slides. Okay, so can everybody see the slides? Okay, so please stop me and ask questions. There's no hurry. Please stop me at any point in the talk to ask questions. So this talk is called Physical Metaphors for Graphs, and it's very much in the spirit of what Dr. Agarwal said. It's about interaction between three different academic disciplines. And these are the three disciplines. So the first one is mathematics, which there are many definitions of mathematics. One definition that I like is that it's the science of necessary conclusions. But the types of objects that mathematicians think about are things like equations, theorems, proofs, and so on. So that's one field. The second field is physics. And physics has a different goal. It's not a science of necessary conclusions. It's about using mathematics to describe the actual natural world. And the types of things people study in physics are laws describing physical phenomena, such as laws of mechanics, heat transfer, electricity, and things like that. And these laws are usually some kind of mathematical equations. Then the third field, which is related to these, is computer science, which is a much more recent field. And this can also be defined in many ways, but one reasonable definition is it's largely about the use of digital processes to solve computational problems. And by digital, I mean discrete, that computer programs are discrete in the sense that they have steps. They're not continuously varying objects like the objects of physics. And the type of thing that the central notion in computer science is arguably the notion of an algorithm, which is a set of steps for mapping inputs to outputs in some specific way. For example, you could have an algorithm for sorting a list of numbers, or an algorithm for finding the shortest route between two places on Google Maps or something like that. So these are three different fields, and both of them have clear connections with mathematics. So mathematics is obviously related to physics because physics is written in the language of mathematics. And mathematics is also related to computer science because this is what we use to analyze algorithms. And this talk is about the question of what is the connection between computer science and physics. So what is the connection between algorithms and these mathematical descriptions of the laws of nature? So, are there any questions about this basic premise? Okay. So I'm going to try to illustrate this in the context of a specific type of object called a graph. So I'm going to start by telling you what a graph is. Okay, so a graph it's a mathematical abstraction which captures the notion of a collection of objects and pairwise relationships between some of those objects. So formally, a graph consists of a set of nodes or vertices, that's just some set, and a set of pairs of those nodes, which are called edges. So we usually depict a graph like this. We draw the nodes as just points and the edges as lines. This is also called a network. This is just the intuitive notion of what a network is. So the important thing to note here is that the essence of the graph is just which nodes are connected to which other nodes. The details of how this graph is, visually represented, this is not a part of the definition of the graph. So, for example, here's a graph. I got this graph from Facebook. I looked at a bunch of my friends on Facebook, and what I did is I made a node for every friend, including myself. So I'm at the center, and these are some of my friends on Facebook. And then some pairs of these friends are also friends, right? So I put an edge between any two people who are friends on Facebook. So, for example, you can see that I have an edge to all of the other people because I'm friends with all of them. And the others, some of them are not connected, some of them are connected, and so on. So this is called a social network graph. Now, again, as I was saying, this is just a drawing of the graph. This graph is the same as this graph. Okay, all of these are the same because they have the same set of nodes and the same set of edges. So there's a distinction between a graph and a drawing of a graph. Okay, so this is, if you haven't seen this before, it might be slightly tricky. So please stop me. Anybody have any questions about this? Okay. Now, this is a social network graph. These come up a lot, but graphs come up in many different contexts. For example, if you are an electrical engineer, then you see graphs all the time when you draw electrical circuits, where the terminals in the circuit are the nodes and the resistors, let's say these are DC circuits, the resistors are edges. Or you see graphs all the time when you look at maps. So this is a picture of a map from the Cold War. This is a Soviet rail network in Eastern Europe. And the nodes here are cities and the edges are rail lines. And so two cities are connected in this graph if they're are adjacent in this graph if they're connected by a rail line. And okay, the internet is a graph, right? The nodes are, computers, and the connections are, network connections between them. And so the point is that a graph is this single mathematical concept that's able to model all of these very different applications in, all these different things that I showed you are actually very different, aspects of life, but they can all somehow be modeled by graph. And of course, these also come up in biology, chemistry, and other areas like that. And so the reason why it's interesting to study graphs is if you can discover something interesting about graphs in general, then that can be applied to all of these situations, for example. Okay. So what I'm going to be talking about is algorithmic questions about graphs. So in which you're interested in, given a graph, you want to compute some feature of the graph. So here's an easy question about a graph. Given a graph, how do you find the node with the largest number of neighbors? Well, I mean, that's not that hard, right? You just count. So, here there are some nodes that have one neighbor, there are some nodes that have two neighbors, and there are some nodes that have three neighbors. The ones in the middle have three neighbors. And so this is an easy question to answer. These nodes have three neighbors. Okay, that's not that interesting. Here's another interesting question. How many hops do you need to go between two given nodes? So this is the type of question that needs to be solved every time you go on Google Maps and try to route from one place to another. So for example, here's a graph. Here I give you two nodes, S and T. And then the question is, how many edges do I need to traverse to get from S to T? So does anybody see the answer here? I don't know how easy it is for the audience to participate, by the way, on Zoom. Is that even possible?
Actually, Dr. Nikhil, I think we'll take questions in the end. That is the usual practice. So maybe by then
you'll take them in the end. Okay.
Yeah.
Okay. Okay.
That
so okay. Mm-hmm. Okay. Well, in this case, okay. So how do you solve this problem? Well, you start at S. You look at the vertices that are one hop away. Then you look at all of their neighbors. You get all the vertices that are two hops away. And now you look at all of their neighbors. You get all the vertices that are three hops away. And since this T appeared in the three hop neighborhood, this is the number of hops needed to get from S to T is 3. So, okay, it's important, but it's not that mysterious how to solve it. So what we're going to talk about in this lecture is other problems on graphs, which it's not so clear how to solve them. I'm going to discuss 3 problems. One is drawing. So if I give you a description of a graph, I tell you the nodes and the edges, how do you draw it in the plane with few lines crossing each other? That question is going to be called drawing. Another question is inference, which is, suppose I give you a graph and now the nodes are labeled with some kind of information. Like let's say, it's a social network graph on Facebook, and somehow how likely each person is to click on a particular type of ad. Then suppose you know this information for some people, how do you extrapolate it to the other people? So this is a type of problem that tech companies have to solve all the time. And then another problem is clustering. Given a graph, how do you group the vertices into clusters that are well connected, but have few connections going out? So for example, in a friend graph, this would say, how do you find the friend groups? If I just give you a giant group of people and I give you their social network, how do you find the friend groups? I'll define all of these more precisely later on, but these are the three problems that I'm going to consider in this talk. And these are algorithmic problems that people actually want to solve on a regular basis. Okay, so now I'm going to move to the second item. So I've told you about graphs, and I've told you three algorithmic problems on graphs. And I'm now going to show you how to solve these problems using ideas from physics, right? So far, there's no physics. These are computer science questions. I'm going to show you how to solve them using ideas from physics. Okay, so let's look at algorithmic problem one, planar drawing. So here's a definition. A graph is called planar if you can draw it in the plane, so on a two-dimensional sheet of paper, without crossing any of the edges. And so the question, algorithmic question here is, given a graph as input, the question is, how do you find a drawing in which the edges don't cross? So for example, suppose I give you this graph. Okay, so I want everybody to take a moment to think, is there a way to draw this so that the edges don't cross? So what I mean is you can rearrange the nodes any way you want. You can move them around. Is there a way to draw this so that any two nodes are connected by a line, but none of the lines cross? So if you think there's a way to do this, raise your hand. Okay, if you think there's no way to do this, raise your hand. How many people think there's no way to do this? Okay. So do most people think there is a way to do this? Okay. Well, since anyway, I hope you got a moment to think. Oh, wait, sorry. Do you have a question? I guess we're taking questions at the end. Okay, so we'll just do raising hands for now. Okay. Okay, so the answer is there is a way to draw this without crossing any edges, right? You just draw it like this. You just move that vertex in the end to the middle, and then none of the edges cross, and it's the same graph because it's the same pairs are connected. So the question is, how do you solve this problem in general? And this problem comes up a lot in, for example, visualizing networks. You want to draw them without all the edges crossing. So that's the algorithmic problem. And what I'm going to show you is a way to solve this using physics. And this problem can be difficult, right? If I give you this graph, for example, it's not so easy, right? Not so clear. Can you draw that without any of the edges crossing? Okay, so let me explain how to solve this problem. So the metaphor I'm going to use is springs. So in high school, you might have learned about Hooke's law. Okay, so what's a spring? A spring, okay, we interact with springs all the time. So the essential feature of a spring is that it has some equilibrium length. And if you pull the spring or compress it away from the equilibrium length, there's a restoring force. And that restoring force, F, is equal to minus kx, where x is the displacement. This is called Hooke's law. I guess we learned this in maybe 9th grade or something like that, right? Okay, so the idea is, let's view the edges of a graph as being springs. So that's why I'm calling this a metaphor, because a graph is not a physical object, right? But let's imagine for a moment that it was a physical object. So what I mean is, yeah, so this is Hooke's law, right? So F is equal to minus kx. If the spring is at equilibrium, there's no force, and otherwise there's a restoring force. Okay, so the metaphor is I'm going to take a graph and imagine it to be a collection of springs. So on the left, I have a graph. And now I'm just going to say, let's just imagine that this thing is a spring. Each edge is a spring, sorry. So the advantage of doing that is now when you have a bunch of springs that are connected, you can do physical experiments on them. For example, I could nail down some of the springs and let the rest of the springs just settle, right? Because in real life, I can do this. I can take a collection of springs and I can stretch them and I can see what happens. So this idea, okay, ignore this equation. This idea is very powerful. I'll show you an animation how it works now. So I'm going to use this to do graph drawing, okay? So what's the input? The input is a list of nodes and edges. That's a description of the graph. Output is an embedding of the graph in the plane. And here's the algorithm. So you take the graph, you start with an arbitrary drawing of the graph, like this one. This is not planar, right? Because the edges are all crossing each other. Then you choose three triangles. You choose a triangle in the graph. Let's assume a triangle exists. And now you nail the ends of the triangle, the endpoints of the triangle to you nail them down in the plane to an equilateral triangle. Okay. Okay, so now the next slide, the next animation is very important. So remember, if the edges are springs, if you do this in real life, it's not going to stay like this, right? It's going to bounce around until it reaches some equilibrium. And so let's see what happens when you do that. So watch this. So you nail these down. Okay. So if you let these springs minimize energy just according to the laws of physics, you get something that looks like this. Right? You started off with something that was not planar and kind of a mess, and you just let physics do its thing, and you end up with something that looks like this. And this is planar. Right? So, I mean, this is kind of amazing because you're using a physical process to solve a computational problem, which is drawing a graph without crossings. This is not an accident. There's a theorem, a famous theorem due to Tutt, which says that if you give me a planar graph, then if you do this spring process, this will always give you a planar drawing. Okay, so you're using a physical process to solve a computational problem about drawing a graph in the plane. And so, by the way, it doesn't have to be a triangle. Just for fun, you could pick even these four vertices connected by a cycle and do this. And then if you again let the springs just minimize energy, you get a different drawing of the graph. Okay. So this is, I haven't told you the proof. This is not obvious at all, and it's not supposed to be obvious, but it can be shown that this always happens. So anyway, what's the punchline? Well, I mean, the punchline is you use a physical process to solve a geometric problem, which is drawing. And the point is that this physical perspective gave us a new idea for how to solve this problem that really isn't that natural if you just think about it as a computer science problem. So this was the first example. Okay. So now I want to show you one more example with the same spring, where springs come in a different kind of a way. Here's the second problem. It's called inference. Now, inference is the problem of you're given a graph and let's say you know some data for some subset of the vertices. So for example, just for concreteness, let's say you're interested in, will this person donate money to X, like where X is some cause? And let's say that, some people said no, some people said yes. You only know this for some of the people. By the way, this is actually what happens online on social networks, right? And then it's of interest to figure out, well, what about the people you don't know, right? What about these other people? Okay, so there's a way to, there are many ways to solve this. This is like one of the basic problems of machine learning, But one way which was proposed and which works reasonably well is the following. You take the vertices for which you know the outcome and you nail them down. So you nail the red ones to position 0 and you nail the blue ones to position 1. And now you again imagine that the edges are springs. And then you just let physics do its thing. So you get some embedding of the graph between 0 and 1. Okay. And now the point is that these are numbers between 0 and 1, and you can view them as probabilities that the person will, yes, donate or not. And this is, this is a statistical problem. I haven't told you the statistical backdrop here. But, there's so ultimately you get, for every node in the graph, you get a number between 0 and 1. And ultimately you can prove a theorem. This is the famous work of these authors, that under certain assumptions, this correctly solves some kind of statistical inference problem of predicting how likely unlabeled nodes in the graph are to have a particular outcome given some labeled nodes. Okay, so this is another example where you started with a statistical problem and you solve it using this physical metaphor of springs, which turned out, and then you ultimately prove a mathematical theorem saying that this actually works. But this physical metaphor was useful because it gave this kind of not obvious idea. Okay, so that's the first physical metaphor. For the second one, I want to talk about another problem, which is called clustering. So clustering is a problem that comes up a lot. As I said, it's a problem of, how do you find friend groups in a given social network? So this graph is taken from a famous paper from 2002, in which they studied US college football games between teams in the year 2000. So in this graph, the nodes are different US colleges, which I guess play football against each other. And the edges are pairs of teams that have played a game with each other. So apparently, in this U.S. college football league, in this college football, whatever setup, the teams are organized in different leagues. So there's some number of leagues, I don't know, like 10 or something, and the teams within a league play more games with each other than they do with teams outside the league. And so the question is, if I just show you this graph and I don't tell you what the leagues are, I just tell you who played with who, can you find what the leagues are? And the reason you might think you can do this is that, teams within a league play more games with each other than with teams outside the league. So this is, it's kind of like this problem of finding friend groups in a social network. It's pretty much the same type of problem. So the question is, given this, just given the pairwise edges between nodes, can you find the clusters in this graph? Okay, so I have to define what a cluster is. A cluster is a set of nodes with many fewer edges going outside than staying inside the set. So let's just say for concreteness, it has 5 times fewer edges going out than staying inside. So for example, in this picture, if you look at this blob on the left, that would be a cluster because you can count the edges. It has lots of edges inside, and has very few edges going outside. On the other hand, this collection of 3 vertices, the 3 nodes in the middle of the graph, this is not a cluster. Because if you count the edges, there are actually very few edges inside, right? There are very few connections inside. Most of the ones are going out. Okay, so this is the question. Given the graph, how do you find the clusters? Or given a vertex, given a node, how do you find a cluster containing that node if it exists? So this is the second algorithmic problem. And again, this is a very widely solved problem in practice. Electrical engineers solve this problem. Statisticians solve this problem. It actually comes up in many different areas. So again, we're going to solve this using physics. So the second metaphor we're going to use, and I'm going to call metaphor B, is heat flow. Okay, so what's heat? So heat is, I'm not going to define it formally. Well, it's something that we all experience. And what do we know about heat? Well, it flows from hot to cold until an equilibrium is reached. If you take a hot iron, like in this case, and put it in contact with some other object, then heat will flow until they both reach the same temperature. Fine. And again, there's a physical law that describes exactly what happens. It's Fourier's law of heat conduction, which says that the rate of change of temperature is proportional to the deviation. The rate of change of temperature at a point is proportional to the deviation of that temperature from the average of its neighbors. So, for example, here are some cartoons. So here's a picture of a situation. So the vertical axis is temperature, where I have a point and it's surrounded by points of higher temperature. Well, its neighbors are at a higher temperature. So according to this law, the temperature is going to go up. Whereas if I have a situation like this, where the temperature is just steadily increasing, and at a point in the middle, actually the temperature is not going to change, because it has one on the right-hand side, it has a higher temperature, on the left-hand side, it has a lower temperature. And here the temperature is going to go down. So this is Fourier's law of heat conduction. And there's some equation, which I don't want to get into, which describes how this works. It's some differential equation, which relates the temperature at a node to the temperature at the neighbors. And it describes how that changes with time. You don't have to worry about the details too much. There's just some equation that describes this. Okay, so now how can I use this to solve a graph problem? Well, let's look at how heat flows on two different physical objects, which in this case are two different donuts. So I'm going to start by heating a small patch of this. So white means it's heated to a high temperature. And then I'm going to let the heat distribute. So let's just watch what happens. So this is what happens. Okay, this is consistent with presumably our experience, and certainly with that equation, that if you heat up a small piece of this donut, then the heat flows according to this law of heat conduction, and it radiates out like this until everything becomes the same temperature. Okay, but now let's look at what happens on this other donut, which is sort of a very thin, it's much thinner. Well, in this case, again, we can heat up a small patch of it and just let the heat radiate. Okay, so eventually it reaches everything reaches the same temperature, but it's taking a long time to heat up the other end, right? I mean, if you run this again, well, okay, I don't know how to replay this, but yeah, like this. Then the heat kind of gets stuck when this object has very thin kind of bottlenecks, right? So the observation here, the sort of qualitative observation, is that the heat flow gets stuck at bottlenecks. So it didn't get stuck here because there's no bottleneck because it was very fat everywhere. But in this case, it got stuck, right, at these bottlenecks. So now the idea, which which is kind of interesting, is let's try to do this on a graph. And let's see if we can use this to find clusters. So how do you talk about heat on a graph? Well, you imagine that every node has a temperature at every time. And now you heat up the node whose cluster you want to find. So you raise the temperature to some temperature. And then the point is that these equations describing the way the temperature changes, they can be applied to this graph, even though it's not a physical object. So maybe at 0 seconds, the temperature looks like this. In 1 second, yeah, you apply this law, the rate of increase is proportional to deviation from the neighbors. The neighbors get a little bit warmer. And then you do it again, and then the heat travels through the graph, right? This is not a physical object, but you can still define heat flow on this graph. And you keep doing this. And then the idea is that, well, if there was a cluster, the heat should get stuck, just like in that example I showed you. If there was a set where there are very few edges going out, the heat should get stuck. So after a short time, if you choose all the warm nodes, you should get a cluster. So this is the idea. This is a second physical metaphor on graphs, that you can define a notion of heat flow on a graph. We believe heat should get stuck when there's a bottleneck, and maybe you can use that to find clusters. So let's see how that, okay, so there's a theorem. There's now a theorem by these authors saying that if there's a cluster, this will find an approximation. But let's just look at an example. Let's go back to our, sports example to see how this works. So here's my graph. I've now colored the vertices depending on the temperature. So I've heated up that one vertex, and everybody, and now actually black means there's no, the temperature is 0. And now if I run heat flow on this graph, this is what it looks like. So see, the heat kind of gets stuck at a few of the vertices. Eventually, it moves throughout the graph. But for a long time, the only warm vertices, you can kind of just see it with your eyes, is this particular set that's kind of, staying yellow. Okay, and so the theorem says that actually doing this heat process will find clusters when there are clusters. So you can check that this thing that the warmest vertices here form a good cluster. They don't have many edges going out. And okay, now, if you run this on some other vertex, you get some different set, right? So in this one, if you run it, you actually see that the heat flows out much more rapidly, right? A lot more vertices are becoming yellow in the second example, because the heat seems to have gone everywhere. And in this case, well, that's because actually there is no good cluster, because that particular college actually didn't belong to any league in this particular case. Okay, so anyway, the bottom line is that you can use this heat process to find clusters in graphs. So you're using a physics process to solve a computer science problem. Okay, so that's all I wanted to say about the physical metaphors. And the summary is that, there are these physical things happening in nature, like springs and heat, but they make sense on these, digital objects, which are graphs. And running these on graphs can lead to solutions of interesting graph theoretic problems, namely drawing prediction and clustering. So we've turned a discrete problem into a physical problem. That's kind of the, the high level theme here. Okay, but that doesn't, if you actually, want to write a program to solve the problem, maybe this is not enough, right? Because, if I want to, find clusters in a graph, I'm not actually going to make some physical replica of the graph and then heat up the temperature, right? I'm not actually going to do that. So how do you actually solve these physical problems efficiently? So this is the final topic, which is how do you simulate physics? Okay, so it turns out that you can simulate physics efficiently on computers. Why is that? Well, I won't bore you with the details. The high level is all of these things are defined by equations, right? Hooke's law is an equation. If you have a bunch of springs, you get a bunch of linear equations. If you're familiar with this, then you can look at the equation. if you don't want to look at the equation, don't look at the equation. It's just that there is some simple equation that describes how springs actually work. And similarly, there is a system of linear equations, right? Similarly, there is some simple equation that describes how heat flow works. It's also a certain kind of linear equation. It's a differential equation, but it's a linear equation. And the common feature of both of these equations, so if you look at the type of equation, if you just look at the structure of these equations, what's the common feature? Well, the common feature is that the equation relates what's happening at a node to what's happening at its neighbors. Okay, so this is the common theme. In both of these physical processes, when you look at a physical process on a graph, you get a system of equations, but the equation always relates what happens at a node to the average of the neighbors. That's a very specific type of equation. It's called a Laplacian linear system. And you know, so really what this is telling us is you started with a graph problem, you turned it into a physical problem, but now you turned a physical problem into a system of linear equations, which is a linear algebra problem, which is something, you know, we learned in high school. And sort of the real surprising thing that has happened in the last 20 years is, I won't look at the details, is that there are extremely efficient algorithms for solving these type of linear equations. So if you're a computer scientist, this means something to you. You solve this linear equations in n log n time for a graph on n vertices. If you're not a computer scientist, or if you're not familiar with what this means, this means it's a very, very efficient, fast algorithm. It means that there's something special about these equations that you can solve you can solve them very quickly on a computer. Now, this theorem, this result of Spielman and Teng, this is a deep theorem. It requires a lot of math to prove this. But again, you can prove that there is an algorithm that very efficiently solves these equations. And so finally, the conclusion is, okay, this is a graph of efficiency. Ignore this. The conclusion is, you started with a discrete problem, you turn it into a physical problem, you turn that into a linear algebra problem, and then you could solve that very, very quickly. And indeed, the best known algorithms for these problems in computer science come from doing this, come from turning it into a physical problem. So anyway, that's a summary, that there are these two worlds of graphs and linear equations, and somehow physics is the thing that bridges them, these physical metaphors on graphs. And yeah, there's this connection between all three subjects that works in a very effective way. So one is that you can use physical processes to solve problems on graphs. And this perspective gives you new algorithms that you wouldn't think of. And more generally, it's just this general principle in math. If you think about the same object from different perspectives, you get different ideas. And it's very powerful. So that's it. So yeah, please, any questions? I can go back to any slide.
Thank you, Professor. It was a knowledge-filled lecture. Yeah.
Hello.
Yes.
Myself, Dr. Rajesh Singh.
Oh, hi.
Department. So I wanted to ask that you applied this spring network. You represented an edge of a graph by a spring. So can we do a similar thing for weighted graphs also? And what kind of impact will it have?
Yeah, it's a great question. So the question was, going back to the spring metaphor, which was a while ago. What I did is I replaced every edge as a spring, right? And the way I define graphs, either edges were there or they weren't there. Now, in practical applications, often you have weighted graphs in which the edges can have a weight. They could be heavy or light. And the question was, can you represent them as springs? The answer is yes, very naturally. You just let the spring constant be equal to the weight. So light edges are very light springs that can stretch a lot. They don't have much effect, and heavy edges are very tight springs.
Okay.
Yep.
So there is another question that the heat flow that which you applied for finding clusters in a network. So can we do a similar thing for some disease network or like COVID network, something like that?
Absolutely, absolutely. In fact, people have been using this to find clusters in disease networks also. So this approach has been used in biology and epidemiology, indeed. So that's kind of the beauty of graph theory, that once you prove something like this, you can use it in any context that you like.
Thank you.
Hello, Nikhil sir.
Oh, hi.
I'm Dhruv from Applied Psychology. And I saw that there were many processes being employed on the nodes and the network. But the first step would be making the graph. So how is that done?
Yeah. So making the graph, right? So that depends on the application, right? So in the 3 examples I showed you, so this graph, yeah, in this problem, the graph just came from somewhere. I don't know where. But let's say, for example, let's say you wanted to draw a social network, right? Then the graph would come from, let's say you look at Facebook and you do like what I did in my very first example, right? The nodes are people and the edges are friends. Or it come from any of these sources, right? It depends on the application. It could be a transportation network, for example. It could be an electrical network. I mean, somehow the question of where does the graph come from is a modeling question, which depends on the application. What I'm trying to convey here is that regardless of where the graph comes from, this always works, right? Like this spring drawing stuff. If I give you a graph that comes from a social network, I can still do this. I can imagine that it's a bunch of springs, and I can still use that to solve this problem, right? So yeah, so the answer is it depends on the context, and it could come from here. It comes from some statistical context. Here it comes from these games. It could come from an epidemiology network. It could be anything. Even psychology, I think people, well, okay, I don't know what's like. Maybe in neuroscience, people look at graphs that come from the brain. So yeah, that's a mathematical modeling question.
Thank you so much, sir.
Hello. So
Hello.
I have one question. Good afternoon, sir.
Good afternoon.
I'm from the Department of Environmental Sciences. And since you are here with us, so can you suggest some of the ways by which mathematics can be applied in teaching environmental sciences? Especially when it comes to earth sciences. Though there has been use of mathematical models in climate change, but in case of earth sciences, if there can be any use.
Well, I guess I should ask you. So I don't know much about earth sciences. So I mean, what well, I don't know, what sorts of things do you teach there that could be mathematical?
So in general, also you can suggest some of the ways by which it can be used. Though in earth sciences, there's distribution of earthquakes, volcanoes all over the globe, the theory of plate tectonics, continental rifts, the existence of continents, etc., etc. Disasters.
Yeah, I mean, I don't know. The 2 roughly kinds of things I can imagine are, one is, I guess physics is obviously important in earth sciences, since so many of these things are physical processes, so it should come up there. But another way in which it comes up maybe more often is just in interpreting statistics or in mathematical modeling, right? That like rate of, like how fast is the environment changing? This is something people are obviously thinking very hard about, and presumably they have to come up with some mathematical models to make these predictions. I guess that must be one of the areas.
Yes, it is. Thank you.
Hello, sir. Good afternoon.
Oh, good afternoon.
First of all, I'm very thankful for your such informative lecture. Sir, I want to ask just one question. Please read on the slide of cluster definition. The cluster definition. Sir, here you use the term of outgoing and ingoing. edges. But the graph theory there that I have studied thought that the graph should be directed graph. But in the cluster, I don't find the directed graph. So
Yes.
please elaborate this because I do not.
Yeah. So it's a great question. Okay, so I should have maybe explicitly said all the graphs in this talk were undirected. Okay, so the way I defined an edge in the beginning was it's just a pair of vertices, right? I didn't specify a direction. So everything I said is for undirected graphs. Now, your question, so okay, if the graph is undirected, this outgoing, ingoing, you're right, I didn't define it. I should have defined it. Ingoing just means an edge between two nodes that are inside the cluster. Outgoing means an edge where a node is inside and one node is outside. Now, indeed, you could ask what is the right way to do this for directed graphs? And that is a very active research question. That is not solved. Directed graphs are actually much more complicated. So for example, yeah, I mean, it's because directed graphs, it's hard to find physical metaphors for directed graphs. I think some people have tried to use diodes, like semiconductors, but it hasn't worked yet. But you're right, it's a great question. But does this answer your question?
Yeah. Yes, sir. Only I just wanted to figure it out because I was thinking not studied much graph theory, but the term outgoing and ingoing just panicked me. So I just only that asked.
No, that's a very good question, and I should have defined it. I mean, I didn't define it, so yeah.
Thank you, Nikhil. This is SP Agrawal. Though I'm not a mathematician, actually I'm from management finance area. You very well started with maths, connection of maths, physics, and computer science, statistics, electrical engineering. And then you explained the theory of graph and the problems, where graph theory can be used, and then the simulation technique. And I can very well understand, that how you connected it with the examples of social networking, marketing network, transportation problem, clustering using football team. This is very much clear. But another important aspect is that I think this theory of graph can also be used, like my colleague asked, in environmental science, can be used in humanities, social sciences, and languages. Can you think of any example or applications in those areas of graph theory? Thank you.
Yes, so I believe it is used quite a bit. For example, in sociology, in fact, they have been studying social networks for decades. And I think now with the internet, sociologists look at these networks quite a bit, and they try to figure out things like find the clusters, like what are there sociological theories explaining why the clusters are like that, and so on. In linguistics, this has been used. Actually, it's been used in music theory. I don't remember exactly how, but yeah, it has been. It's been used in music theory to classify different, to try to see if you can classify pieces of music by genre automatically. For example, you look on. Well, okay, this is not music theory. It's used by Spotify, for example, where what you do is you make some sort of a graph out of looking at what people listen to, and then you use it to try to predict what they're going to listen to next. And I mean, okay, the underlying graph is probably because they want to incorporate social information as well as just your musical history, right? They believe that you probably will like things that your friends liked or things like that. Actually, that's probably not what you're asking though, right? I don't know the specifics, but I do know that this is being used in linguistics and musical theory. I think there are, Yeah, I mean, I can try to send you some references later. I'm not sure right now.
Thank you. I think you are perfectly okay that see, when we search something on Google, they immediately understand our taste, and like you said about music, what really we want to listen to or what we want to hear to. So I'm sure that they must be using the application of graphs. So thank you very much.